In this class, we're going to consider how you determine the local extrema of a function. So there's a little bit to unpack there before we get into the sort of technical details. So extrema refers to the extreme values of a function, which basically is code for like the highest value and the lowest value, which is represented by the highest and the lowest point of the graph. But if you're considering a graph like, for example, this kind of cubic function, so I've drawn a part of that graph, but in reality, like a lot of function graphs, this carries on upwards forever and it carries on downwards forever. So we can't really talk about the extrema of this function in a general or global sense because it has no extrema, it has no maximum or minimum value. So that's why we're talking about the local extrema. And local extrema just means that we're going to restrict the part of the graph of the function or the values of the function that we're allowed to look at. So let's say that I put a couple of kind of construction lines on here in my red pen to represent the part of the function that we're interested in looking at. So we're only looking at the values of this function represented by its graph in this part of the graph here, okay? So on that part of the graph that we've restricted ourselves to, that local part of the graph, there is an extreme value. Well, there's two extreme values, there's a maximum and a minimum. So this point here is the highest value of the function. Remember, the values of the function just mean the y values, okay, the output values. So the highest point on the graph represents the maximum value, and the lowest point on the graph represents the minimum value in that range of values, okay? So in that local range. So it's really important to know that we're only talking about a local extrema here. So how do we then go about finding these? Well, we've kind of in recent classes been defining or connecting, I guess, the derivative with the gradient. So if we move around this curve, we know that at each point on the curve, the slope of the curve, or more accurately, the slope of the tangent line to the curve at those points as we move around is changing. And in particular, we know that when we get to these turning points, which are also called critical points or stationary points, when we get to these points, which are maximum and minimums in this case here, we know that the slope of that tangent line goes to 0. But another way of saying that is the derivative goes to 0. So if this function was, say, f of x, at this point here, this maximum point, f prime of x, the derivative, is equal to 0. And the same at this point here, the minimum point, f prime of x at that point is equal to 0. And it's the fact that we know that the derivative equals 0 at those extrema points, those critical points, those stationary points, those turning points, however you want to call it, they all kind of mean the same thing, then this is the fact that we can actually use to help us find those points. So to take these examples, which are in different formats slightly, all we're going to do is differentiate, set it equal to 0, and then solve the subsequent equation. We don't have to think about the graph of these functions, and that's one of the really cool things. We could, and if we represented the graph, if we drew the graph, if we sketched it, we would see the behavior that we're looking at. But if we just trust the algebra and trust the derivative process, then that is fine. We don't need to actually worry about the actual geometry. So let's just go ahead and get into this example. So if we just start by taking our derivative, so dy dx, just using the power rule for this one. Now, how you take the derivative obviously just depends upon the function. It doesn't depend really upon the fact that we're trying to find extrema. There's no particular derivative technique associated with that. It's just whatever you need to use. So this guy and this guy are polynomial functions. We're going to use a power rule. This one over here requires a chain rule. But the point is just to take your derivative however you need to take it, using whatever technique is applicable, setting it equal to 0, and then solving the subsequent equation. So using the power rule here, we're going to get 6x minus 12. Now, we know that the key is that at these points we're interested in, the derivative is set equal to 0. Now, you might be encouraged by a teacher to write in a sentence here, something like, I don't know, like 4 for local extrema or for critical points or for stationary points, you can word it a few different ways. For local extrema, dy dx equals 0. Just to clarify why you're going to set that equal to 0. Then you just go ahead and take that derivative and do what you said you're going to do, set it equal to 0, like this, which will then give you generally a fairly straightforward equation to solve. And you could rearrange this one, and if you did so, you would find that x equals 2. Okay, so that is the x coordinate of the critical point, the local extrema. Now, if you need to find the y value, if you need to actually find the extrema, depends how the question's worded. It could be worded in various ways. If you actually needed to find the value of the function at that point, you would just sub that back into the original function, and then that would give you the actual value. But in this case, let's just assume that we've been told just to find the x coordinate of the extreme point. Now, just thinking a little bit about the geometry of this function. Now, I'm not going to get into it too much and draw an accurate sketch, but this is basically a quadratic function which will give you a parabola graph. And not only is it giving you a parabola, it's giving you a parabola which is this shaped, which is one which has got a minimum turning point. So what we've actually found there is the x coordinate of this minimum point. It's that point where the tangent line would have a gradient of 0. So we know the x coordinate of this point is 2. And if we needed to find the y coordinate, like I say, we just put it back into the original function. But notice as well, and this is really, really important, we only got one solution here. We had a linear equation, one solution, and the original function was a quadratic. Now, a quadratic can only have one extreme value. A parabola graph can only have either a minimum turning point like this or a maximum turning point like this. So it can't have any more than one extreme value. When you move to other function types, it's always worth considering, hey, what kind of function is this? Therefore, what kind, how many points should I expect to find? Now, if you look at this guy here, this is a cubic function. A cubic function is generally shaped like this one I've got here. It's going to have some kind of shape like this, which means that it's going to have probably 2 critical points, 2 local extreme values. Doesn't always have that. You can get some very simple cubic functions which only have 1. And in fact, in the next class, we're going to look at these types here, which are called a point of inflection, but they tend to be more of a special case. Generally, because we're differentiating, we're powering down, because the power rule says to power down by 1. This means that our derivative is going to be a function not with a cubed in it, but with a squared. In the same way this one went from a squared to an x to the 1, this is going to go down to a squared, which is a quadratic equation. So we're going to get a quadratic equation here. If we solve that, we should get 2 solutions, which ties in with the geometry of a cubic function. Okay, so it's good to have that expectation. So let's take our derivative, dy dx. Again, we can just use the power rule. So the 3 multiplies to the 1/3. That's quite convenient. That's going to give us a 1. So we don't need to write that. X goes down to an x squared, or x cubed goes down to an x squared. And then we get minus 4x minus 12. Now I'm just going to skip this line here and be a little bit cheeky and just go straight on to the next line. So x squared minus 4x minus 12, that is our derivative. To find our local extrema, our critical points, we're going to set that equal to 0. Now this we would need to factorize because it's a quadratic equation, unlike our linear equation here, which we could just kind of solve directly. So putting this into 2 brackets, hoping that it does factorize or else something's gone horribly wrong. 6 and 2, these questions will usually be designed so that it does factorize. And we would need a minus 6 and a plus 2. And if we solve those, we're going to get 2 solutions. X equals negative 2 and x equals positive 6. So those would be the 2 x coordinates of the local extreme points of that function. Okay, and one of those would be a local maximum and one would be a minimum, just because of the geometry of these. They can't obviously both be the same, that wouldn't make any sense. One of them has to be above the other. So one would be the max, one would be the min. In this class, we're not going to determine which is which, but we will be looking at that in another class, and that's called the nature of critical points, or the nature of stationary points. Okay, so moving on, let's take a look at this guy. So similar technique, it's just that this one needs the the chain rule for us to differentiate it. So casting your mind back to the chain rule, if you've already seen that, hopefully you have. So we're just going to multiply, well, just actually to hold up for a second, the chain rule is applicable to composite functions, which is what this one is. This is an overall cubed function, but it's got an internal quadratic function there. So it's a function inside a function, which makes it a composite. And for composite functions, we use the chain rule. So multiplying the 3 in front, leaving the bracket basically the same, powering the bracket down to a squared, and then multiplying by the derivative of the inside. The derivative of the inside is 2x minus 2, okay, like that there. Now, we need to then just do the same thing. We need to set that equal to 0. So a little bit more work to do in this one for sure. So if we go 3x squared minus 2x minus 8 to the power of 2, and then 2x minus 2 equals 0. So that's our derivative. We'll set it equal to 0, and then we need to go ahead and solve that. Now, we could divide both sides by 3, which would just basically get rid of the 3 there and kind of tidy it up a little. And then we're splitting it off into sort of 2 equations. We've got 2x minus 2 equals 0. Now, I should say at this point, actually, this is not a standard function type. Like, I've got no idea what the graph of this thing looks like. So it's not like these two here where you can say, this is a parabola, we're going to get one extreme value. This is a cubic, you're probably going to get 2, and you can kind of just quite, and I mean, you'll see a lot of those, and you can expect the solution you get. I've got no idea what this thing looks like. It looks quite hideous, to be honest, so I don't know how many points we're going to get, but we'll soon find out. So just splitting it off into 2 equations, we get x squared minus 2x minus 8 squared equals 0. This one is just a linear equation. We can just solve that to get x equals 1. The second one's kind of a quadratic with a squared on it, so a little bit ugly. If we square root both sides, the square root of 0 is just 0, so we would just end up with x squared minus 2x minus 8 equals 0, so not too bad. Now it's a quadratic equation. We expect 2 solutions from that. Hopefully it will factorize into 2 brackets. Questions which turn into quadratic equations, which a lot of questions do, especially in calculus, obviously are designed so that the quadratic equation factorizes. Okay, you could sometimes solve this without it factorizing by doing other things like completing the square or using the quadratic formula, which is effectively the same thing, but generally they're going to be designed to factorize. So why am I telling you that? Because if you get to this point and it doesn't factorize, that's almost certainly going to be an indication that you've done something wrong earlier in the question. I always tell students that as much as they often hate these little quadratic trinomial equations, they're also really, really useful and powerful because they tell you 9 times out of 10, probably more, they tell you whether you've done the question right. If this factorizes, I'm pretty sure I've done it right. If it doesn't factorize, I've almost certainly done it wrong. So this one does factorize, and we get solutions x equals minus 2 and x equals 4. So for this kind of more out there function, we've ended up with 3 critical points, which would be the x coordinate again of the local extreme values. And again, we've only been working here with the x coordinates. If you actually needed to find the y coordinate, the local extreme value, if you like, the up and down value, the y coordinate, you would just sub the value into the original function to get that value. So for example, going back to the first one, if we put a 2 in there, we're going to get 2 squared is 4, 3 times 4 is 12, so that's going to be 12. 12 times 2 is 24, so it's going to be 12 minus 24, which is minus 12. So that tells us that the full coordinate of that point is 2 minus 12, and that means that this point here was actually at 2 minus 12. So this is the value of the function at that point. The y coordinates are the values, but this point here is the local extreme point. It really depends how your question's worded. It could ask for the x coordinate, could ask for the y, could ask for the full point. Just play around with different question types to determine that. So basically, just as a quick recap, finding local extrema really just means finding maximum and minimum values. These are examples of what we call critical points or sometimes stationary points. They're basically turning points on the graph. And to find those, we just use the fact that at those points, the derivative is equal to 0. And how we find that derivative just depends upon the function, Polynomial functions will be the power rule. Something like this thing over here, we had to use the chain rule. So it's pulling together quite a few techniques. So not easy, requires a bit of practice, but that is true of most of the calculus techniques. So make sure that all makes sense to you, both the theory and how I've gone about those examples, and then check out a few practice questions of your own.